Good day to you. This is Galactic broadcasting to you on Friday, February 10th, 2023. This is an informal introduction to today's lecture series. Yesterday I had promised to continue the lecture series. That was not possible, but now it is. What we have over here is a couple of graphs. You've seen them before if you've watched prior videos, but I never assume in any video that any listener has even heard of any prior videos. I don't redirect people who listen to my videos to any other source. You're getting everything from me in the lecture. In other words, you don't have to go back and crib. I'll summarize everything. Science is nothing if not the art of summarization. One of the major problems in astrophysics and quantum mechanics today is the inability to explain anything that they say. They can't even describe reality, let alone explain it, and those are two different steps. What I'm going to do now in this informal introduction to today's lecture series is describe these two graphs that you see, which look similar, do they not? The top one, which has a sepia background, is a Boschkovich curve. It's a very special form of the Boschkovich curve, which I've identified as being the source of all the wisdom that comes through geometry, through the work of rational scientists, in attempting to explain the universe in any way, mechanically, dynamically, or geometrically. One does need visual resources. And this sort of a graph, which is a 2D graph, is very well suited to our onboard system, which is linear. The whole point of my thesis overall, at the highest level, what am I doing to contribute to science, has to do with this curve. The ability to visualize reality. It doesn't look like it's up to the task, does it? Because it's so simple. This is a two-part curve. That's easily seen. It hardly needs explanation, but actually, the core of scientific understanding is the ability to reduce complicated and complex information to its simplest form. The simplest form. That is always visual. Always visual. And as I have been very careful to point out, although again I don't expect you to know that, I'm just reiterating, a blind person, a person blind from birth, is in no way crippled for visualizing reality. The system is embedded by DNA coding. It's partially linear, but as I've discovered, it's also spherical. That's been proved by neurophysiology in my lifetime. There's more information that I could add to that, but accept that we see in two modes, and we've only ever used one. Now, in our daily life, we use both. Linear vision is innate to us. It's why we see orthogonality. This is miraculous, and it's rarely discussed as such. But the foundation of geometry is in part the straight line, although I've discovered that we also have a fully operating spherical system. We don't have a number system for it. Actually, I've discovered what that number system is. It's a two-component number system, And that is my discovery that I need to explain, first by describing it, and then explaining it. And that means reducing my discovery to a visual realization that anyone can see. That's the meaning of this curve over here. Over here. The lower graph, which you can see has much higher resolution, it's obviously not a pen drawing, that's from Wikipedia. It's the graph of the nuclear force. That graph is the key to understanding physics and mathematics and the universe. It's the key to everything. That is what I'm going to need to show you. The proof sequence for spherical geometry has already been described in previous lectures. I'm not going to go through that, not even quickly now, because that discovery of the spherical number system for spherical geometry for spherical physical space is the single most important discovery in modern times. I claim that. A claim such as that is nothing but hot air without what you see over here to our left. And so I'm going to begin there. This is off the cuff. I have basically just awoken today. And I'm going to go out and get myself another shirt and tie. I'm going to be well dressed. I do have a haircut, and I'm trying to look as good as I can, but I am 68 years old, so you're going to have to suffer through seeing this. I'm sorry. But be careful, because if you're angry because I'm ugly and mean, part of that is due to God's blueprinting. Don't forget that. If you're ever making fun of someone for their skin color or something else that they were born with, like they're retarded, which I sometimes appear to be. I don't think I am, but who knows? You never know from the inside. But you're blaming God. If you use the N-word of some human because they have dark skin, you're blaspheming God's name. You can't be a racist. You can't even like it. You can't even tolerate it if you're a rational man trying to be wise. Which you'd better be or turn this off. So this curve over here, over here, he's actually over here for me. Oh shit. Actually, it's over here. Oh God. It is over, well, whatever. I am a little retarded. It's actually dyslexic. I don't even want to say that of myself because I'd be blaspheming God's name. I shouldn't call myself retarded. That's blaming God for my problems. Well, if I'm retarded, frickin' fix it, Sam. So this is how I'm attempting to fix my own life. There's nothing short of that. A wise man wants to get to heaven. And we're not willing to wait. We don't care about death. Death and life. We do care about life, though, because that's where we're at. We're not in death. We're in life. And so it's time to fix everything while we have a chance. Seems impossible since no one else has done it. Well, one guy did, a guy named Yeshua. He did it. He made it. And then they murdered him, and then he had to leave or they would have murdered him again. Well, that's going to happen to you too if you got the right stuff. But don't worry. Heaven will help you. That's what I'm here to be part of. My little part. So, in this informal, impromptu, off-the-cuff, spontaneous presentation, introduction to what we're going to be covering today in a series of lectures when I look a little better and I've showered and everything else, I do want to follow up on yesterday's lecture where I promised there would be a series to follow. There's all kinds of technological things I have to attend to. I'm a one-man operation. I've had trouble with email and comments, which I have one commentator. And he's attempted to email me, and I told him I had set up email, and sure enough, I finally found where the emails were going to. But the comment system for YouTube, maybe it's great and I just don't understand it very well, but I take this commentator very seriously. He's made a couple of excellent contributions to my studies, and he's interested. I mean, that's the whole idea of science is communication. So I spent quite a bit of time yesterday following up. I just noticed, man, I ignored him again. He left another comment that I didn't see for 3 days. That's unacceptable. So forgive me, I do have a lot of details I have to attend to. I'm also improving my anagalactic.space site. I've been promising to have PDFs and links and everything else, documents, diagrams. I've promised GeoGebra stuff. I've promised geometric algebra stuff. None of that's been happening because I discovered Roger Boshkovich's curve. And you know, when it rains, it pours, right? Well, none of this is bad, but I do have to apologize. I am only a finite creature attempting to understand the infinite universe. But as I taught you, it's not infinite. There is no such thing as infinity, and that's the meaning of this curve. Let me explain as simply as I believe is possible from my aspect and from your aspect. Is there anything that I can say about this curve to convey what I know about it that's going to help you? That is what I'm going to try to do now, and keep this under 20 minutes. And then we'll have a series that's going to be excruciatingly precise. More precise even than numerics. With numbers you can fudge, and in fact that's part of the problem profile in astrophysics and quantum mechanics today, is linear algebra is ill-equipped to deal with spherical space. And as I began by saying in this impromptu off-the-cuff lecture, the universe is spherical. I've proved that. That was the nature, one aspect of the discovery sequence that I endured through the year of 2022, leading to close to 300 videos. A rare sequence, actually, if I may just put in a plug. If you want to go back and see any of those videos, just to see a sampling of what I went through. It was an endurance test that actually, it's not easy. A discovery sequence is not easy, or everyone would be doing it. But without digressing too much, let's look over here and see these two curves. The top one is Boshkovich's curve, which he executed with his pen 2.5 centuries ago. The curve below it you see is similar. There are some differences, but the curve below it is from a Wikipedia article on the strong force. In the simplest description that I can conjure for what these curves mean, consider them to be the same. They are the same, although they're describing slightly different things. The curve can be read from right to left, and it can be read in one of two ways. It's relativistic. And it would have to be, since it's 2D. It's relating the y coordinates to the x coordinates. You're familiar with that. That's a typical graph. But what is it describing? It's the force relationship between two particles. The lower image is the relationship between two protons at femtometer range, which is the smallest unit of measurement known to man, useful to man. There's nothing smaller than a femtometer. You could say there is, of course, because it's infinitely divisible. Another aspect of the paradox. How can something be infinitely divisible? Well, actually, that is a direct contradiction and basically summarizes the quantum mechanical paradox. But it's more all-embracing than that. This is the fundamental problem in physics, is the limitation of linear algebra in describing a spherical universe. The Greeks encountered this, and everyone since has encountered it. It's the reason for the calculus. The calculus is to get at curved space. But you're still using lines. This graph, and I'm considering these two to be the same relationship, the top one is the relationship between two particles, which is more generalized solution mode, is more robust. The bottom one is extremely specific. It's the relationship between two protons in nuclear space, which is not atomic space. It's smaller than atomic space. They're both measured in femtometers. But you may know the relationship, the geometrical relationship, really the volume relationship between an atom and a nucleus. It's extraordinarily small. Inside, the nucleus is small compared with the atom. I could give you figures, but those tend to not be significant. Not at this level. We simply want to know what this means. What does it mean? What is this curve? The relationship between two protons, referring now to the Wikipedia image at the bottom, that is the relationship between two nucleons. Now we're forced to say nucleon instead of proton because you've certainly heard of the neutron. I want to give you a clue that's going to help you enormously in your study of nuclear geometry and nuclear mathematics. This is simply subatomic particle physics. That's what it is. It's the study of the center of the atom. The bottom graph shows the relationship between two nucleons, but I want to simplify that for you. You can completely forget about the neutron. And I've already described why you can get away with that. It's a mnemonic. Because, of course, the neutron is quite real. But the neutron and the proton are so closely related that the only difference that subatomic physics can ascribe to describe the difference between the neutron and the proton is in one of a few ways. One is charge. The neutron is said to have no charge, and relativistically speaking, that's undeniable. The proton is considered to have a positive charge with respect to the electron. But as for what the proton is not in respect to the electron, the proton has a relationship with other protons. And it goes quite deep. Obviously, this is as deep as you can go. Going in is the proton. There is nothing smaller than the proton. So let me begin there to give some bracketing information, because you may object to that because you've heard some claims made by the subatomic particle physicists. Mostly this is just a matter of interpretation of what's being said. The neutron, excuse me. The neutron and the proton are exactly the same weight, except for an extremely tiny difference in weight. And what does weight mean? It refers to mass. It's a unit term for mass, is weight, which is actually quite complicated, and it's the only 3D SI unit that I've encountered. The rest being two-dimensional, we say. With units, the word dimension has a slightly different meaning than it does in geometry. I'm sorry to go down a rabbit hole here. I don't mean to guide you away from my main topic. But science is rigorous, and it's always a compromise in explaining what you're saying as you're explaining something bigger. So I hope this helps you, but the neutron and the proton may be thought of as exactly the same particle, and we know that from the quark system. It has been said, and here's my point, my sub-point, is when I say there's nothing smaller than a proton, referring to the proton is that they're almost exactly the same. What makes them different? They do have an extremely tiny difference in weight. Extremely tiny difference. But they are virtually the same particle, and that has been proved by the subatomic particle physicists, is both particles can be construed mathematically as having 3 parts inside. These are always called particles. There's a reason for that. Quarks are called particles, and you can get away with that. It is linear algebra, so you're going to have some ridiculous terms because it's linear, and you're not describing a linear space. So you're going to have to compromise somewhere. The way that the compromise is executed, and it's worked fairly well, there's nothing wrong with a linear algebra approach, as long as you know its limitations. But the limitation that faces subatomic particle physicists is the nature of a particle. And because measurements are really all we have, really, to describe these things, the measurements that we can take of a proton or a neutron reveal that you could say it this way, so I'll say it the way they say it, is that there are 3 particles inside the proton, and there are 3 particles inside the neutron. These are called the up and down quarks. There's 2 types of quark, and just to throw in something you may notice, you'll hear the term antiquark, so that makes 4. Disregard that, it's a mathematical complication. There is such a thing, but it's mathematical. And that is my point. The quarks are not particles, and in fact they've never been isolated. So what do they mean? Is it a chimera? Is it a misconstruction? No, it's not a misconstruction. But you're encountering a limit in your ability to name what you see. And you have then a choice, and it's the wave-particle duality, believe it or not, at its most fundamental level. And in fact, that's what this curve describes, just to let you know, we're not off track here in our discussion of the proton-neutron relationship. It is critical to understand that in another context. So I'm giving you bracketing information to avoid any confusion that you might encounter when I keep referring to the proton as if it were the only nucleon. Technically, of course, that is a mistake. There is the proton and there is the neutron, and they are definitely different. The way that they're different is on a 2-1 harmonic in the relationship between the up quarks and the down quarks. For a proton, it's 2 up and 1 down. But if you reverse that, let me do this, and just there. Think of one of these as being up and the other one as being down. You can have 2 down, 1 up, that's a neutron. 2 up and 1 down is a proton. If I have it backwards, it makes no difference, unless it has to make a difference because they are different. But I can't remember which one is which because I'm slightly dyslexic that way. But either way, the point is it's a 2-1 relationship. A neutron has 2 this kind, and a proton has 2 the other kind. So it switches. And that's the only difference. And that's why a neutron can change into a proton. And it wants to. But there is such a thing known as beta decay, where a proton spontaneously decays into a neutron. This has to do with the weak force, and we're not going there because we're not really interested in subatomic particle physics, although we certainly will be. What we're interested in now is force relationship between two particles. The upper Boshkovich curve shows the relationship between two particles according to his conception of what is a particle. And since he had no conception of a particle, it was way too early in scientific history to be talking about particles. He never did. Although he did. He just didn't call it by exactly the same name as particle physicists call their particles, which, as I've already indicated, they're not quite sure what is a particle. That is the quantum paradox. What is a particle? Ha! Well, there are two distinct particles. The proton with the neutron, but they're related, so closely related, I want you to think of them as the same thing. The proton does have a charge, though, so it does have a very important charge relationship with the electron, and that's the other particle. As a simplifying concept, I want you to adopt what I'm going to tell you right now, because I've adopted it and it works. You always have a footnote with these mnemonics, but trust me on this one. There are only two particles in the universe. That's a bold statement, okay? The whole point of the subatomic particle physics program, including the Hadron Colliders, is to discover more particles. The reason for that incentive or directive is particle, 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 particle. Why is it always particle? It seems like at a certain point, pardon the pun, you can't really say it's a particle anymore. Well, when you encounter that limit at its extremum, that would be either the proton or the electron. In that respect, the electron is simpler. It's a fermion, and that means that it has no internal parts. There's nothing smaller in terms of a particle than an electron. But the proton has a mechanism inside. They're not particles, though, and in fact, the Hadron Colliders have proven that fact. But you see, now they're in a bind, because now they don't know what to call the quarks. Are they particles or not? Well, if they are, you have a contradiction. And if they're not, you have no idea what to call them. Well, I do. They're mathematical relationships based on motion. It's the fundamental motion in the universe is what's inside the proton. I'll just tell you straight up that that really is why we have Hadron Colliders, is to get inside the proton. That's the goal. So far, the results are rather extraordinary, and they've been acclaimed by no one less than Richard Feynman, that it's the most precise form of science ever discovered, is quantum electrodynamics, which goes to quantum chromodynamics. The chromo is an artifact of human language having to do with color. Color has nothing to do with particles, but they ran out of words. And so quantum chromodynamics is simply a lower level of quantum electrodynamics. Now, in terms of these graphs over here, the one that I want you to be looking at is the one that's a little easier to read, I would have to say. It's quite a bit more polished. I've highlighted it there. That's the relationship between two protons at femtometer range. On the lower axis, the x-axis, these would be the abscissae, according to Boshkovich's terminology, which is Latin, sorry. But the abscissa numbers, you'll see range from 0 at the far left all the way to 2.5 femtometers. So this is describing a range between a linear separation between two protons of about 2.5 femtometers, which is 1/10 of 1/4 of a centimeter. If you read it right to left, you can read it either as a pure force relationship with no velocity involved, or if you're like me, you might prefer to see this as the path of a proton toward another proton. If the proton were going to go toward the other proton this way, it enters the graph right about here, and then the graph dips, correct? That's deceleration. And so the ordinates, that is the y coordinates, which are in newtons, you'll see that from 0, well, actually not 0, but from negative 2.5 force units to the median, which is the middle horizontal line. That's the median of force, which is 0. That would mean that there is no force relationship between the two, which means that as a proton comes in, it's not really being affected by the other proton, but actually that would be a mistake to say that, because you'll notice that it's an asymptotic curve to the median, or, reading right to left, an asymptotic curve with respect to the median line. That blue line, as it enters from the right, is not on the median. In other words, that particle is always affected by the other particle. All the way to infinity, it's never on the median line with respect to the force relationship. In other words, every proton is force related to every other proton in the universe. Which might boggle your mind. It certainly boggled the minds of all the top physicists, so you can be forgiven if that sounds a little bit odd, because it raises the lazy 8 infinity of force relation between every particle in the universe and every other particle. That fact alone has led to the mini-worlds theorem, or theory, it should be called. I won't go there right now, but we're going to be covering that in great detail, because we're going to solve these problems. I already have, but not... Science is progressive. You can always get better, and believe me, this is the cutting edge right here. This is a graph of the curve of infinity. Everything on this graph is infinite with respect to linear algebra. That's where we get the idea of infinity. It's the number, if you want to call it a number. It's not a number, though. Infinity is exactly the limit of what a number is. It's actually beyond the limit. And I showed that yesterday. If you haven't seen that lecture, you might want to look at that lecture, The Collapse of the Circular Function, another Boshkovich curve. But this Boshkovich curve is the core. This is the graph of reality. I want you to notice some very simple things about this graph. Nothing is straight. And in fact, linearity such as science is forced to use, it's the only system we have is a linear system. It's ingrained in us, so it's not unnatural, but it does have a severe limit called infinity. And infinity does not exist in the universe. It's not a physical concept. It's a human limitation concept based on our linear visual perceptual space. We have two. We also have a spherical perceptual space, but we don't have a geometry for it, and we don't have a number system for it, so we can't really use it for computation. That all changed last year when I made the breakthrough discovery to a new geometry and a new number system, which is quite difficult to prove. It's a fish ladder sequence of paradoxes to get to spherical space. No man has ever been able to penetrate that limit. The Greeks could not, Einstein could not, Feynman could not, and no one to this day has been able to break free into the other, far more explanatory spherical number system and spherical geometry that I have proved is exactly what the universe uses for her number system. Citing Max Planck and a host of others, this is collaborative, but the discoveries made by Einstein, Planck, Dirac, Emmy Noether, even Maxwell, of course, and Boshkovich, who preceded them all, they each got a part of this. But none of them were able to transcend the barrier between linear and spherical space in order to do what science does with geometry and with computation. We have to have both. It turns out that's a given. If you have a geometry, you have a number system. That was proved in my lifetime indirectly by John Horton Conway. He proved what is a number for the first time in human history in my lifetime. What is a number? We finally got a definition, far beyond anything Cantor could have imagined. And it's a wonder that Conway didn't lose his mind. But he did it, and it was recognized by no one less than Donald Knuth of Stanford University, who awarded a name to this new number system, the surreal numbers, which I think is delightful. It's taken from Salvador Dali. I don't want to get too far off here because we're at 37 minutes. This curve, to close this out, this curve, the relationship between two protons at femtometer range, I'm going to explain to you what this means now. Read it right to left as a proton coming to another proton, which is on the vertical axis to the left. You can think of the proton as being anywhere on that line. It's not at zero. It's anywhere on the line. It's interesting, but that's a limitation of linear geometry. In 2D, is it looks like that proton should be at 0, 0. It's not. It's anywhere on the ordinate axis. So this is a visualization of an approach of a proton to another proton with a velocity. You don't have to think of it that way. This is a pure force relationship, but it can be read in two ways, and I prefer to read it this way, although the force relationship is actually the best. But we're just going to step down a second so we can read this as humans to see if we can understand it. I'm going to show you how to understand this. The proton approaches from right to left. It's heading straight for the other proton. For whatever reason. In a hadron collider, there's a proton sitting waiting, and another proton is being accelerated in a cyclotron, and focus so that it's going to collide with the other proton to explode them to see what comes out. That's what a hadron collider does. And this graph shows what happens when they meet. This is the meeting of the two protons. So this proton could be coming in from right to left at sublight speed in a cyclotron. Or it could just be hanging out and it's being attracted. That doesn't make sense though, because protons repel. Actually, there's more to be said about the relationship between two protons. What happens when they collect at the center of an atom? What is the relationship between the protons? This graph describes the relationship between the protons in the nucleon. In the nucleus. So the force relationship between the protons is described by this curve. However, it's only described in one part of the curve. The part at the far left where it skyrockets. What is that? In order to compromise on the force relationship, velocity relationship, which are two ways of looking at this, think of the proton as having a relationship with the other proton where this proton is approaching the other proton. For whatever reason, impetus force or not, velocity or not, it's just a proton that's approaching the other proton for whatever reason. It's decelerating. That's what's happening. It's being repelled. So this is a diagram of the repulsive force between two protons because they're both positively charged. This is a simplification on a particle-particle relationship, but as I'll be showing you, this applies to all particles. Believe it or not, it does. But this is the simplest relationship between two particles, two protons, at the core. What does that look like? Say you have a nucleus with one proton, and here comes another proton. What happens as it approaches? Well, it's repelled, so it should not be able to reach the other proton. Can it? This graph tells us it never reaches that other proton. Never. They cannot mush. They cannot mush. They can't bleh together. On impact, they skew. And what does that mean? This is the quantum paradox. And now I want you to be prepared for something that's actually going to change your neuronal configuration. This is a very serious insight, so I want you to concentrate on this. It's queer at this level because what we're trying to do is get a simplification, and ultimately the barrier that we face in understanding the relationship between these two protons is that they cannot collide. They never touch. But what do they do instead? Why do the protons hold together in the core? They should be repelling each other. Why don't they? Nobody's ever answered that. Let's see if we can answer it now. On approach to the other proton, it decelerates because of a repulsive force, but when it reaches the extremum, this is the minimum of repulsive force, you'll see down here where it reaches that curve that looks like it comes down on a circular curve, and then it reaches the bottom and then immediately goes on another asymptote. That's the asymptotic relationship between the two particles. They never meet. And the meaning of the skyrocketing is that you've now switched from the space domain to the time domain. That's the reason why there's a horizontal asymptote going back out. As you go out, that curve, if you're going backwards from left to right, going off to the right of the graph, it goes up and up and up, but it never hits the median line. That's the asymptote of the horizontal. The asymptote of the vertical is the other part of the curve way over here where it shoots up. That is asymptotic to time. The horizontal asymptote is the asymptote of space. And this defines infinity. And that's the end of our lecture. That's 45 minutes. I'm going to go get a nice shirt and another tie, take a shower, have something to eat, and then we're going to get into the most excruciatingly challenging insight sequence that you will ever experience in your life. Because this is the solution. And I don't need to finish the sentence. This is the solution. This is Anagalactic. We'll be right back.